Yes. Everybody sees my screen?
Yeah.
Perfect. Thank you. So today, or the plan for this week also would be that today I continue talking about beamlines and optics. So this follows up on last week's last lecture, where we mainly addressed the question how to transport X-rays generated by synchrotrons along a beamline, and how to shape the beam, how to filter the beam to make it useful and focused onto a sample in the end. So there's one more very important component missing that we haven't talked about yet. So this will be the topic of today, and then I will shift towards the topic of free electron lasers, so either today or tomorrow. And then on Thursday, the last lecture of this week will then be the Python tutorials, where you are supposed to play around with a numerical model for free electron lasers. But for now, so today will be still about synchrotrons, but I mean all these main components that we have been talking about you will see are also used and needed for free electron lasers. So it's a good idea to basically study how the physics work and where these different components came from. Because in the end, X-ray free electron lasers are just a next generation, or a new development which is entirely based on synchrotron physics. So this was our main schematic representation of a synchrotron that contains the most important features and components. Mainly the insertion device or undulator, which is the main device where radiation is produced. And so last time we followed the path of the photons that are emitted from the undulator and then propagate onwards through the so-called beamline. And of course, the beamline contains many different components. We talked about the front end components, which are based typically what is called in the undulator tunnel. So that's a radiation protected area where a lot of X-ray radiation scatters off the undulator and the front end devices. So here there's like nobody is allowed to be there during synchrotron operation. And then further downstream, after these initial beam characterization using a beam profile monitor, by shaping the beam, by filtering, doing some rough filtering, typically high pass filtering to get rid of a broad low energy spectrum. Then the beam propagates onward to the beam line, where also users are, where like the radiation levels are low enough that users are allowed to be present. And we talked a lot about mirrors last time, because in the X-ray, a mirror is something much more complicated than the mirror that you have in your bathroom, which is just a silver-coated or aluminum-coated glass plate. In particular, in the X-ray range, mirrors need to be mounted at grazing incidents, like at grazing angles, very small angles. And we looked a bit deeper into the theory behind, mainly, well, the theory was actually a very simple one. It is based on the Lorentz classical harmonic oscillator model that models charges, in particular the electrons in the atoms, as classical harmonic oscillators, and then based on this harmonic oscillator model, we came up with an expression for the refractive index, which is a complex quantity, and it contains a real part and imaginary part. The real part, this is typically what we call the refractive index. So that's the part that acts on the phase fronts, on the phases of the light, and that is what is responsible for refraction, also reflection on dielectric interface or surfaces between dielectric media. But then there's also an imaginary component, which is the component that leads to absorption and to attenuation of the beam. But this is probably quite well known to you for like visible, in the visible range. But in the X-ray, it turns out that the index of refraction has a quite different structure and different properties. So the very generic trend of how index of the real part, so the refractive part of the index of refraction, how this depends on the frequency, spanning over the whole spectrum from long wavelengths infrared to very short wavelengths X-ray. It's shown here. So we have all these wiggles, which of course corresponds to resonances, vibrational resonances, valence electronic resonances, inner shell resonances. Overall, there is this trend of a falling index of refraction, and that actually concerns both the delta and the beta term. So in general, the index of refraction in the X-ray is very close to 1, which is already an important finding, which tells us that it's very hard to make any lens that has a strong focusing property, because the index of refraction is just so small. It's essentially impossible to build refractive lenses with short enough focal length, for example, to build a microscope or an imaging system based on refractive optics, just because the index of refraction is so small in the X-ray. And and this general falling trend, that is due to the general scaling with lambda square. And in addition, we find that the index of refraction can even take values lower than 1, smaller than 1. And that can actually be used. This has a beneficial property, namely we can realize conditions of so-called total external reflection. Total external reflection is similar to total internal reflection, what you know in the visible range, but for typical index of refractions that are larger than 1. But in the X-ray, where the index of refraction can be smaller than 1, there we can achieve total external reflection. And the rule of thumb for calculating the critical angle when total external reflection happens is given here. So it depends on the wavelength and also on the atomic number, so the number of electrons in the atom. But the point is this critical angle for total external reflection is very small. For regardless which material we consider, platinum, rhodium, silicon, or so, and in the full range of X-ray photons, the critical angle is in the range typically below 1 degree. And that means that if we want to exploit total external reflection for achieving high degrees of reflectivity, we need to mount our mirror surfaces at this very small angle. So based on the knowledge of the refractive index, we can calculate reflectivities, and there's this very useful website by Henke where you can look up all sorts of optical properties, including the delta beta, but also reflectivities of materials. And just an example for gold, for the gold surface placed at 1 degree, we can see that indeed for low photon energies, we achieve very high degrees of reflectivity. That would be the total external reflection regime. But then for the higher photon energies going towards hard X-rays, even at 1 degree of an incident angle, a gold surface would not reflect anything anymore, right? The reflectivity goes down to 0. So we need to place the gold surface at even smaller incident angle, something like 0.45 degrees to reach 90% reflectivity at around 1 keV. This is what we were looking for last time. And a very convenient way to place mirrors, both to guide the beam in X, Y, and in X direction and Y direction, so left, right, up, down, but also to focus the beam is this so-called Kirkpatrick Bayes mirror system, KB mirror system, which achieves that and even has positive properties of canceling astigmatism. It's very commonly used at synchrotrons, but also at FEL beamlines. That was the refractive part of N, but N also has this imaginary part, the Ni, which if you place Ni into the typical wave equation, we arrive at Beer-Lambert's law for absorption or extinction of incident intensity. And there, if we plot the transmission, so 1 minus the amount of absorbed intensity, that's the transmission, we find very low transmission, so complete blockage of X-rays in the range. So this is for a 10 micrometer carbon layer, like a diamond window. So there we find complete blockage in the range up to about 1 kilo electron volt, and then a high pass characteristics for hard X-rays. So these diamond windows are typically placed in the front end of the beamline to filter out and suppress all the low energy photons and just transmit the hard X-rays. Yeah, so in general, the extinction coefficient, right? That's the coefficient. That's this coefficient up in the exponent of Beer-Lambert's law. Has in general this property of becoming smaller and smaller for higher photon energies. So as we can see, the hard X-rays are typically transmitted by any material more efficiently than low photon energies, so that the extinction coefficient drops. But then on top of that, there's these interesting steps. And so depending on which material, like beryllium, silicon, or lead, these steps occur at different photon energies, but any material has some kind of steps like this, where the extinction coefficient suddenly jumps up. So can somebody tell me where these steps come from? How can we understand that the extinction coefficient, which is essentially the imaginary part of the refractive index, why does it feature these like steps where the extinction jumps up by like more than an order of magnitude? Can anybody tell me? Where do these steps come from? They seem to be material-specific properties. Like even here in the case of carbon, okay, that's the transmission. This is something like 1 minus the absorption coefficient. But even there, you can see a small peak up here or down here at 300 electron volts, actually, which is, if we would plot or take, let's say, a slightly thinner layer of carbon, then we would see that there's also here there's a pronounced step. So these steps occur for almost all materials. Where do they come from?
Are they absorption age?
Absorption edges, you mean?
Yes, sir.
Yes, exactly. So these are absorption edges, and I mean, where do these? Sure, I mean, it looks like an edge, but what does it mean physically? What's happening in the material at these edges? And you were right, these are absorption edges, but can you just explain in 2 more words what's happening there?
Basically, we are exciting core levels for different materials at different photon energy.
Yeah, I mean, you're saying we are exciting. I mean, we're actually ionizing, right?
Yes.
But yes, we are ionizing out of different inner electronic inner shells. Like most prominently, the most strongly bound electron is the one in the K shell, in the 1s. I mean, you're probably familiar with this notation. K shell means the 1s electrons. L shell is the n equals 2 principal quantum number. M is n equals 3, and so on. And yes, whenever the photon energy crosses the threshold for ionizing an electron out of one of these shells, then all of a sudden a new channel opens where electrons can be ionized, and the material can absorb photons by ionizing electrons into the continuum. So this opens a new channel for absorbing light and undergoing a transition from a bound state into a free ionized state, and therefore the extinction coefficient jumps up because photons can be more efficiently absorbed, and the light gets extinguished. And yeah, so typically for these materials, the K shell, that would be around 10,000 eV. L shell, that's these guys here, and M shell, that's various edges up here. So yeah, this is the so-called ionization edges, and most prominently the K edge is the one occurring at the highest photon energy, because it takes the highest photon energy to ionize electrons out of the 1s orbital. Yeah, it could be a good idea to look at what's happening in air. So I mean, air, as you know, is a mixture of mostly nitrogen with like some 80% nitrogen, 20% oxygen. There's some argon. And indeed, when we scan the photon energy and shine our X-ray beam through 1 centimeters of air, then we will see that the beam gets actually very strongly attenuated. So the transmission is very low in the range, let's say up to a few keV, a few kilo electron volts. And there's again these steps in the transmission spectrum, which are due to the L edges. So yeah, this is absorption of n equals 2 electrons in argon. I mean, argon has only less than 1% of concentration in air, so this is a small signal, but mostly nitrogen absorbs at the K edge, at around 400 eV and oxygen here around 550 eV. Which means that soft X-rays definitely have to travel in vacuum. So you need a good vacuum system, whereas hard X-ray beams actually can be transported even through air, because sure, there is some ionization going on, but the transmission is nearly one at like really hard X-ray ranges. Now, last thing I wanted to look at in more detail is so mirrors. We have looked at them, but this arrangement here, it's called a monochromator. And the monochromators are needed in synchrotron beamlines because although the undulator spectrum has quite narrow peaks, remember that in the undulator there's interference happening, which produces harmonics, where mostly the first harmonic is the most intense, then the second harmonic was very weak, there was a third harmonic, and so on. But even these individual harmonics actually have quite broad spectrum, typically broader than what you need if you want to do high resolution spectroscopy, or also if you want to do high resolution X-ray diffraction imaging based on monochromatic radiation. There we need more monochromatic light. And the way to achieve this in X-ray beamlines is typically using so-called double crystal monochromators. So the way they work is that, like similarly to a spectrometer, in the visible range, we need a dispersive element. So some element like a prism that disperses light according to the color of the light. And only that in the X-ray range, we cannot use any prisms. I mean, first of all, the prism would absorb most of the X-rays. And second, the index of refraction, as we have seen, is very close to 1 of any material. So the amount of the diffraction of the X-rays would be very small. So the only way to diffract X-rays is using a grating. Just like in the visible range, there's diffraction gratings that can be used. But again, the difference with X-rays is that it cannot be a normal grating as we use it in the visible range that consists of a periodic grooves that are artificially made in a metal surface, for example, because the wavelength of X-rays is like the factor of 1,000 or so shorter. So the groove size also has to be very, very small. The groove distance between grooves, like the grating constant, has to be on the order of the wavelength. So angstrom, few angstroms. And now comes the question: how can you make, like in the visible or UV? You probably have seen these various types of gratings that can be used for diffracting light. Maybe some of you even have seen what like blazed gratings. That is a grating that has this specific surface structure, which is made for optimizing diffraction into one specific diffraction order, typically the first or the minus first diffraction order. But where, like in the visible and UV, these artificially fabricated gratings have groove sizes on the order of a few hundred nanometers, right? Has to be on the order of the wavelength. But now in the X-rays have angstrom wavelengths. What would you say? Is it even possible to fabricate a grating like this with a groove size on the order of a few angstrom? Or what kind of device, what kind of material could we use as a grating for X-rays? In the end, we need to fulfill the Bragg condition, right? It's the condition for constructive interference into the different diffraction orders, which means that d, the groove size d, has to be of the order of the wavelength. So d should be on the order of angstrom length. How can we realize such gratings in the X-ray range? With angstrom size groove sizes, how is that possible? Or is this possible to artificially fabricate?
Can we use interference between two beams as some sort of a mask with which we can use to fabricate on any material?
Okay, I did not fully understand what you say, but you wanted to. Did you want to?
Usually, if we are going to fabricate something, we require a mask of that dimension, of Armstrong dimension, a mask,
yes,
which will help us to fabricate these grooves. And to get such mask, we can use the beam itself, the interference pattern between two beams, which will create your the constructive and the destructive interference pattern to create such a mask.
Okay, that's an interesting idea. I mean, you're right that interference patterns between like interfering light beams can actually produce very regular periodic structures in principle. I mean, the problem with trying to fabricate artificially such an angstrom-sized groove pattern is that in the end, this groove pattern should consist of atoms, right? It should be made out of some kind of material, and any material consists of atoms. Now tell me, what is the size of an atom?
Around an Armstrong.
Yes. So what you were suggesting is essentially making an artificial groove pattern like this at angstrom scale, which essentially comes to like placing atoms artificially, like individual atoms, or maybe it could be two atoms or so, but like few atoms, placing them in a regular pattern somewhere. And that obviously is very hard to realize. But it turns, so I mean, the point is we need a grating that has basically spacings between material and missing material on the length scale of 1 angstrom. And the good news is that we don't actually even have to make a lot of effort to produce such structures artificially, because any crystal material, a crystal is made of a regular arrangement of atoms, right? That's a crystal. So we can just use ideally a single crystal, so a perfect crystal made up of single atoms, and we get our diffraction grating just from the periodic structure of any crystal. Yeah, so and that works for wavelengths like roughly below 10 nanometers. There we can find suitable crystal materials where when we irradiate the crystal surface by a polychromatic X-ray beam, we would get refraction, so basically constructive interference according to Bragg's condition into one specific direction at one specific angle. Of course, the light also penetrates with some, according to Beer-Lambert's law, with some exponential damping, it penetrates into the material. So one question is like, how many lattice planes of the crystal do we actually illuminate? So that will determine the width of the reflected order. The more lattice planes we illuminate, and the more lattice planes contribute to constructive interference, of course, the sharper the diffracted beam becomes. But yeah, so that's the method of choice in the X-ray. We just use single crystals. Obviously, the first diffraction crystal that is placed into the synchrotron beam gets a whole lot of heat load, because remember, an undulator in a synchrotron typically emits a few kilowatt of radiation, which contain quite a broad spectrum. So a lot of this broad spectrum, which does not fulfill Bragg's condition and is not diffracted, will just be absorbed inside the material. So this means that the first diffraction grating in such a synchrotron beam absorbs a whole high heat load, and therefore needs very good cooling and good heat conductivity. And typically these gratings are actually, these crystal gratings are water cooled or even liquid nitrogen cooled. Yeah, so here you can see a different like the refraction of at different crystal orientations as a function of the Bragg angle. And like the most used materials for realizing these crystal grating monochromators in synchrotrons are silicon, mostly silicon 111. Yeah, so that here needs to be placed at Bragg angles, let's say in for 10 keV, typically for silicon 111, first order diffraction would there the silicon crystal would have to be placed around 12 degrees or so. So what do you think? Why is silicon the most suitable material for realizing these crystal monochromators? I mean, there's germanium, there's diamond, of course, actually is quite efficient. There's many other possible materials, but you would probably find in the different synchrotron beamlines mostly silicon monochromators.
Silicon is readily available and it is comparatively cheaper.
Yes, exactly. It's like thanks to semiconductor industry, silicon is available in relatively cheap in very high quality single crystals, large single crystals, and also like machining methods are available for machining and like finishing the surface of silicon crystals from semiconductor industry. So that's the main reason. Although, I mean, you can see here on the right-hand side, this is a plot that shows the intensity of the Bragg reflected peaks. And there you can see that the silicon here it actually doesn't have the highest intensity. The germanium produces more intense Bragg peaks. Diamond Bragg peaks are even less intense. This shows the minimum. The number just always shows the minimum photon energy, but this is quite similar. Or if we want to go to the highest hard X-ray beamlines, then it would have to be diamond here. Diamond is most efficient for in the hard X-ray range. But yeah, diamond obviously and silicon can be produced in nearly perfect single crystals. So they are very well suited. Yeah, this is the different color dots here. This is just for different orientations of the crystal. Of course, you can choose different planes from which diffraction should happen in the crystals. And then, yeah, once we have decided for one crystal, silicon, for example, to diffract the incoming beam, then typically it's not only one crystal, but it's one crystal and a mirror arranged like that. Or it many cases also it's what is called a double crystal monochromator, where then two crystals would be placed parallel to one another, and then to change the color, so to change the photon energy of the diffracted first order, for example, then the tilt angle of the crystal would have to be changed. And as indicated here, we would actually, in such an arrangement, change both the tilt angle of the crystal and of the mirror up here at the same time. And actually, even more, we would even change the tilt angle of the crystal, the mirror, and we would even vary the spacing between the two surfaces. Do you have an idea why it has to be this complicated mechanical movement of tilting? I mean, first question, why would you place a mirror or a second crystal parallel to the first one? And then why would you move these two components in this correlated manner? Why not just take one crystal and tilt the crystal around to choose the photon energy, and that's it? What's the advantage of having this arrangement of two parallel surfaces that are tilted in synchronously?
I could imagine if you just had one mirror, the beam path would change, right?
Sure, exactly. I mean, ideally, you want to select your photon energy without moving the beam at all, right? Because, I mean, the monochromator sits still quite far upstream in the beam line, so any small angle variation of the beam would propagate, and you would probably never fiddle the beam all the way through all these apertures and mirrors that come further downstream. So we want to really keep both the angle of the beam and even the lateral offset very constant. And yeah, for that, in this arrangement of like tilting the lower mirror, let's say counterclockwise, then the beam would go further to the left and would be reflected further down from the upper one. So, but by tilting the upper one in the same sense, we can keep the outgoing beam parallel to the incoming one, and then to even take care of the beam offset, we have to actually move the spacing between the separation between the two mirrors. So this actually is all incorporated in the mechanical devices that are used. And oftentimes even either the grating or the mirror, or if it's two gratings, then one of them have this curved shape to focus the beam at the same time. And of course, these devices, these monochromators, are like quite sophisticated, bulky mechanical devices that control all these degrees of freedom. Plus, they need water cooling. So these hoses here, this is for water cooling. Plus, the whole thing has to be in high vacuum. So this is quite expensive and large, sophisticated machinery. So, for example, there is an AMO, atomic molecular physics beam line at the Astrid 2 synchrotron at Aarhus University. This is where Asbjørn and I come from. It's shown here, so very schematically. So there's an undulator that generates the light. There's a first M1, just a bending mirror, deflecting mirror, and then we have the monochromator set up, which consists in this case of a first mirror and a grating. And here you can actually see two gratings. So this is because typically these, if you want to cover a very wide photon energy tuning range, then you have to use different types of gratings. So you can actually like interchange gratings in the setup, and then the beam further propagates. It's focused on mirror M3, and then there are some filters or foils that can be used to cut out higher order radiation, higher like harmonics from the undulator and so on. And this is how such a monochromator then looks in real life. It's a big tank at ultra high vacuum. There's a lot of aluminum foil around. Anybody knows why all these components here, the whole monochromator, but also the beam line behind, why is it all wrapped up in aluminum foil? An
To
aluminum
reduce
foil.
RF interaction?
No, actually not. So, I mean, there is here, this is
More of an electrical insulation.
a good idea, but no. The electrical insulation should be taken care of using proper cables and so on. So it's not electric insulation, it's not RF, it's not like stray light X-rays or so. Has another very practical reason.
To not allow the inside radiation outside?
No. I mean, there's these are all stainless steel containers and quite thick windows, so there is no UV and no X-rays coming out anyway. So this thin aluminum foil would not help much against X-rays coming out if they came out of the stainless steel walls. No, it has another reason, this aluminum foil. So this aluminum foil here is used for thermal insulation. So why would you thermally insulate these vacuum pipes and vacuum apparatuses?
For the baking.
Sorry? Say
For
again?
baking the system.
For baking, yes. So this is ultra high vacuum. So we are talking about 10 to the minus 10, 10 to the minus 11 millibar of pressure, residual gas pressure, so very high vacuum. And to reach very high vacuum, the only way is to bake the whole apparatus. So meaning by baking, I mean we heat up all the pipes, all this vacuum tubing to something like 200 degrees for a few days. This is, of course, with no X-rays going through. This is just for preparation. And by heating up all these surfaces, by heating up the surfaces, start like outgas and evaporate any dirt and any contamination that is present inside the vacuum vessels. So that is evaporated off the surface, pumped away by efficient pumps. And then once the setup is cooled down again, the vacuum becomes very good, because all the contamination is gone. So baking is the method of choice if you want to reach ultra high vacuum. And that needs to be done for the whole setup, including this big tank that houses folding mirror, gratings, water cooling, and complicated mechanics. So this is quite some sophisticated device. All right. Let me. Okay, yeah. Let me then. So we are almost done with these gratings, but there's one more important aspect to diffraction gratings and monochromators, namely, just looking at this picture, it looks like we can just send in our polychromatic beam that contains many colors, diffracted off the crystal surface or of the crystal, and we get a perfectly monochromatic, or at least very narrow band diffracted beam, according to Bragg's condition. And I mean, I just remind you how the undulator spectrum looked like the radiation coming from the undulator. Like most intense contribution is this first harmonic, which is which is exactly what the first harmonic from the undulator. But there's also some second, third harmonic, and so on inside the spectrum of the undulator. And this is the the Bragg condition for diffraction on the crystal. Problem is that the actual Bragg condition is multiples of the wavelength have to fulfill this 2D. Like D is the lattice constant, so D is the separation between crystal lattices that are labeled by HKL. These are the Miller's indices of the different lattice planes. So there is it's integer multiples of the wavelength. And that means that if in our incoming beam there is a component present with half the wavelength, then the same Bragg condition is fulfilled for the second diffraction order for half the wavelength, right? So this is the first diffraction order for n equals 1 would be the first diffraction order, which let's say would work for the first harmonic of the undulator spectrum, but the same diffraction condition holds for the second diffraction order of the grating, provided that the lambda over 2, so the second harmonic of the light, is present. And that unfortunately is present to some extent, because undulators create exactly this comb of half wavelengths, third wavelengths, quarter wavelengths, and so on. So this means that like the third harmonic, which typically is also quite strong, would be diffracted at the same angle and propagate on through the beamline just at the third diffraction order of the grating. And that is a big problem, because this means that this beam here actually is not perfectly monochromatic, but it does contain higher harmonics. So the question, this is an important question, how can we suppress higher harmonics in the beam? And this is actually the same for FELs. I mean, FEL radiation is also produced in undulators, so it also contains higher harmonics. So again, if you want monochromatic radiation, we have to somehow suppress these higher harmonics. But in the X-ray range, there is one thing that helps us. And that was, remember, is total external reflection for angles that are smaller than the critical angle, but at angles larger than the critical angle, then the beam is not totally reflected, and large parts of the beam get absorbed. So this means that while, for example, omega, the fundamental frequency here, for that one, the incident angle is smaller than the critical angle, and we have total external reflection. But for the second harmonic, for that one, that's because the critical angle depends on the frequency. So for the second harmonic, the critical angle will be smaller than the incident angle alpha, and the reflection would be suppressed. And that can be used, for example, for 8 keV incident light at an angle set for 0.2 degrees. There, under these conditions, the fundamental, so the 8 keV, would be reflected with almost unity efficiency, because here we are in the total external refraction regime, but the second harmonic and the third harmonic would be suppressed by 2 or 3 orders of magnitude, right? So this is one way of suppressing higher harmonics in the X-ray regime, which is very convenient, and there's other ways of doing that. But that works nicely in the X-ray range, where we have this total external reflection effect. In the EUV range, so EUV means extreme ultraviolet, so at much shorter photon energies, where some people are interested in doing experiments like Shiva Ramakrishnan and I have been doing a lot of EUV experiments at synchrotron beam lines. There, this trick does not work because there is no total external reflection. But there, the only way is brute force suppressing higher harmonics by putting in some absorptive filter that would filter out the higher harmonics. And it so happens that, for example, for a fundamental photon energy at 20 eV, which is a photon energy that we like to use very much because here we can excite helium atoms and helium nanodroplets resonantly. It so happens that a tin filter, a thin tin foil of 200 nanometer thickness, just has the property of having this transmission window, which transmits some part of the beam, 20%, like better than nothing. But the point is that the second harmonic, which is 40 eV and 60 eV, are completely suppressed. So this is a very nice, like, bandpass filter to filter out to like transmit only 20 eV photons and suppress all the rest. So this we have been using extensively during our beam times. But of course, this is by pure lucky coincidence that there is a filter material, namely tin in this case, that has this property. If we wanted to do an experiment at 30 eV or another photon energy, then we would have to play other tricks. And one other trick that can be played is to build the whole monochromator in a different way. So far we have been talking about these monochromators as the one shown on the top, where does here the beam comes from the left. It's collimated by a curved mirror and then bent by another mirror, grating, refocusing. Then there can be filters and some sample and detectors. But point is, this is going through the grating at some small angle. There is another way of building a monochromator, which is called normal incidence monochromator. Here, the beam is reflected at near normal angle, meaning at almost 90 degree with respect to the mirror surface, and also the refraction on the grating happens at nearly normal incidence. I have to stress that this is only an option in the EUV. For X-rays, there is no mirror that has high enough reflectivity, and also diffraction of the grating in the X-ray would not work at normal incidence. But in the EUV, this is an option, and there's several advantages of using these normal incidence monochromators, namely the good suppression of higher harmonics, just because the efficiency of diffraction of higher photon energies drastically drops when the photon energy goes up above EUV range. So the efficiency drops for higher photon energies. It has very good resolving power. So the degree of monochromatization is very high. So that's very good for spectroscopy. In principle, the mechanical design is easier because we don't need these very long, shallow grazing incidence geometries. In the EUV, we get quite good reflectivities, and also astigmatism is reduced. But this only works in the UV and EUV. So there's a very severe wavelength limitation here. And it only works below something like or above a wavelength of about 100 nanometer, and has also quite small tuning range. Okay, this is what I wanted to tell about monochromators, which are these devices to get monochromatic light for doing further experiments. So now I would suggest, since we have a little bit of time left, we have a little quiz prepared for you to recap what we have been talking about in the previous 2 sessions. And now, Sanouf, could you please guide me on and guide us how to do this, how to start this quiz?
Sure, Professor. I will have to start actually.
Yes, please.
So I think everyone got ill. Only the participants are getting the questions if you've seen the screen.
Get QR code.
The quiz has started. So for you, Professor, if you go to like more options, you can see polls slash quizzes.
I think it takes time to set it up. But
So even right now I'm seeing the QR code, but let me see. Okay. Okay, got it.
Just for confirmation, everyone is able to take the quiz, right?
Yeah.
By mistake, I submit the quiz answering only 2 questions, so I don't know if I can do something.
I think you answered the first 2 questions.
Yeah, just the first 2 questions. Then I press submit.
I don't think so. I can restart the quiz without ending for everyone.
Otherwise, I can do it with Ask Your Mini. It's fine.
Tanup, I think you can share the QR code and they can answer it with another email ID. Can get that for whoever.
Please scan the QR code, and I think you might be able to take it from another mail ID.
So how are you guys doing? Is it still need a minute more, or are you mostly done?
Just a few minutes more, please.
Okay.
I think once you have submitted the quiz, please raise your hand.
Yes, please. Cool. I can already see the statistics of the answers. That's very useful. So, Sanoop, how did you manage to get this into Zoom, like this, the
So
interface
it's a
with Zoom?
feature available in Zoom itself. So
Okay. Is that how do I find this? Okay. There's if I go to more, there's Pulse quizzes. Is that it?
yes, sir. So if you
Okay.
want, you can add a new quiz by hitting on the plus.
Okay. Interesting. Okay. Most people are doing quite well, actually. If I scroll through the answers, there's not much confusion, not so much confusion, a little bit of confusion. All right. Should we stop here and quickly go through the different answers, or does someone still urgently need a minute more? Rajni, is it okay if we continue?
Yeah, sure.
All right, then Anoop, should I share my screen and so I can quickly scroll through the different answers or the statistics?
If you want, and you can also know people who answered what also.
Oh, how can I do that?
So I'm ending the poll now. So
Okay.
share result.
Okay.
So I think everyone is able to see their answers.
And then why don't maybe I could quickly share my screen and then we can have a quick look together to see what questions might
Yeah.
be ambiguous. Yeah, I mean, question one, undulator transitions, that's exactly the strength of
I don't think
undulator.
so. That screen is being shared.
Oh, sorry, good. Thanks for mentioning. Okay, but am I not? I'm not sharing the right screen, maybe. Share.
Move to 107 and
Do you see the poll now?
not really, sir.
Huh, interesting. I thought. I have to. Let's see, which screen do I have to choose then?
Yeah, now we can see the poll, right? Is this from your
But
side?
it's personal action. So,
Okay, okay.
Okay, but I mean, Anup, if you could share the
yes, sir.
poll, then because for
Once.
some reason it doesn't show mine on my screen.
Okay, so is it visible?
Yes, perfect. Yeah, I mean, question one, it seems that's clear. So undulator radiation, that's the strength of undulator radiation, that it's a free transition. So we have full freedom to choose the wavelength. Yeah, go down. I can move it. Okay. So does everybody see this? The poll? I'm moving it now.
Yeah.
Okay,
Yeah,
perfect.
it can be.
Yeah.
Yeah. So number two, yes, synchrotron radiation is emitted from wigglers, bending magnets, undulators. RF accelerators actually are not meant to emit radiation. Those are actually meant to absorb RF radiation into the electron beam to accelerate the electron beam. So that's not a photon source, but all the other three are. What's the difference between wiggler and undulator? Everyone answered correctly, except for there was one or two answers about undulators producing shorter pulses. No, that's not true. The time structure is the same for undulators and wigglers, and that's just given by the electron bunches. So the pulses emitted by any insertion device at a synchrotron are always like 10 to 100 picoseconds, so rather long. There's little we can do to get shorter pulses. So it's not by no means ultra fast in the usual way of operating synchrotrons, at least. So for short pulses, we need FEL. And the leading term, I think most people did it right. Some people picked the theta term, but the leading term definitely is the one that has the undulator wavelength and the gamma square Lorentz factor. That is mostly correct. So mainly the important answer of like what the K, the undulator parameter depends on is the magnetic field. And actually also the, what was the answer? Answer D was also correct. That was, what was it again? Okay, anyway, this is...
That's undulator periods, lambda U.
Lambda U, yes, the undulator wavelength is also correct. Yeah, so the emitted power scales as E square over mass to the fourth power. That C is correct. Higher harmonics are emitted due to anharmonicities of the electron trajectory. That's also correct. Apple type is tunable polarization undulator. That's correct. You can increase coherence by, yes, 3 different ways. That's correct. synchrotrons have 2 rings, but only one is operated in synchrotron mode, and the other one stores electrons over long periods of time. That's correct. Synchrotron, the name comes from the fact that in the original synchrotron operation, which is also used in the booster ring, particles are synchronously accelerated and more strongly confined by the magnetic fields, so that the orbit of the electrons stays constant. And that is the answer. Okay, so here was some confusion. Because it as the so it's answer D is correct. Answer C, because particles are synchronously accelerated as they are decelerated by emission of radiation. This is what's happening in the storage ring, but this is not what is actually meant by synchrotron operation. The physics is correct. In the storage ring, the electron bunches are constantly accelerated because they constantly lose energy through that radiation. That's true, but this is not synchrotron operation. This is storage ring operation. Microtron, answers A and D are correct. That one was completely correct. What's meant by the top-up mode? Electrons are periodically accelerated to keep the energy in the storage ring constant. The physics is true, but that's not what is meant by top-up mode. So top-up mode means electrons are periodically injected into the storage ring to keep the ring current constant, right? So basically the storage ring is constantly topped up with fresh electrons, because electrons are constantly lost due to collisions with the residual gas in the storage ring, also because some electrons drift away towards the walls of the chambers. So there's an exponential loss of electron beam current over time, and to compensate this loss, the electrons have to constantly be or periodically be refilled by re-injecting bunches of electrons into the storage ring, and this is what is called top-up mode. Typical duration and separation of pulses is all correct. Perfect. Okay, very nice. We have another 10 minutes time. Then I would say let's use this time. In 10 minutes, we could just about get started. Okay, no, 10 minutes, it's maybe not worth starting with a new topic of free electron lasers. Then let me just spend the last 10 minutes on presenting a few applications of synchrotron radiation, and then we start tomorrow with the free electron laser topic. So here, in the last 10 minutes, we'll continue following the photon beam further downstream. So just before we talked about the monochromator that produces monochromatic radiation. In the end, the photon beam is supposed to interact with some sample, and we want to detect some signal, right? So to probe the sample, that is the main application of synchrotron radiation. And just to get started with this, in principle, there is, very roughly speaking, 2 ways of doing experiments at synchrotron beamlines. One is detect photons. And here mainly the most commonly used method is detecting elastically scattered photons, or we can also say like diffracted photons from some mostly crystalline target. So this is X-ray XRD X-ray diffraction, XRD, X-ray diffraction. That's one of the most commonly used techniques, and this is for structural imaging of targets, of crystals or macromolecules, and actually macromolecular, so it's also called MX, but MX is the same as XRD, just applied to macromolecules. Mostly we are talking about proteins, so protein structure imaging is the most important application of X-ray synchrotrons nowadays. And also for X-ray free electron lasers, this is becoming the most important field of application. But of course, you can study single crystal surfaces. There is resonant X-ray scattering. There is small angle X-ray scattering, which are variants of elastic scattering. There is inelastic scattering, like resonant inelastic X-ray scattering. RIX is an important technique. But of course, we can also detect photons that are emitted by fluorescence. We can detect photons that are transmitted through the sample, and do this even with some spatial resolution, then it would be microscopy. Or we can just detect the amount of X-rays reflected from a surface. So this would be X-ray reflectrometry. This is the different, I think, quite complete list of different techniques that use photon detection. On the other side, we can detect like the product of the interaction of X-rays with matter, which is mostly electrons, most photoelectrons and other secondary electrons that are produced by X-ray interaction. Also, in some cases, ions. And when you detect electrons, and mostly with energy resolution, then we are talking about spectroscopy. And nowadays also this can be combined with spatial resolution to do microscopy. And there, like typical techniques are X-ray absorption near edge structure. That's called GIAN. It's one technique where we study the edge, the structure near the edges of inner shell or core shell ionization of different materials. A very related technique, it's called extended X-ray absorption fine structure, EXAFS. This is about the fine structure. We can just measure the energy of photo-emitted electrons, which is the topic of XPS, X-ray photoelectron spectroscopy, and that actually is synonymous of ESCA. ESCA stands for electron spectroscopy for chemical analysis, same thing. We can do this in an angle-resolved manner, then it would be called ARPES, angle-resolved full electron spectroscopy, or in combination with microscopy, then this would be photoemission electron microscopy, or PEM. And so these are the main techniques of doing spectroscopy and or microscopy by detecting mostly electrons. So just to give you one first brief glimpse of how it works. In the case, the simplest case would be X-ray fluorescence. There we shine our X-rays on a sample. This ionizes and like core shell ionizes, core shell excites the sample, and the holes that are produced in the inner shells would be refilled by electrons from higher lying levels, refilling these hole states, and that emits light. And this light, of course, can be both in the X-ray, but it can also be at shorter wavelengths if the transitions are between neighboring levels. But all this light can be dispersed on some dispersive element like a crystal, as we have used it in the monochromator in the first place to produce the monochromatic light. In this case, the crystal serves as a dispersive element, like in a spectrometer, to disperse the polychromatic fluorescent light emitted by the sample onto some detector. And for example, X-ray fluorescence spectrum, spanning the range of a few kilo-electron volts here, for some clay sample that contained a very small amount of cesium atoms. There, by looking into this characteristic emission lines of the different materials, we can actually identify smallest amounts of different elements that are contained in some sample. So this can be used as a very sensitive analytic tool to analyze the composition of some samples. But more important technique than fluorescence spectroscopy is diffraction. And diffraction is actually the same as interference of the diffracted waves or the scattered waves on the different scattering sites. And if this is a crystal with a periodic lattice arrangement, then we can calculate the path difference between the individual rays, right? And by demanding that the path difference 2 times d sine theta equals integer multiples of the wavelength, we arrive at the Bragg condition. And this Bragg condition actually it can be formulated in a different way. Namely, is the so-called Laue condition, which we can relate to the Bragg condition by considering the k vectors. The k vectors are the wave vectors of the incident light field and the diffracted light field. So k in and k out. This is about elastic scattering. So the length of the vectors should be the same. And the connecting vector, so the difference between k out minus k in, that is called the q vector, or the momentum transfer vector. And in this picture, there is a famous condition for constructive interference, which is called the Laue condition. And the Laue condition tells us that the difference vector here between out minus in, which is the q vector, has to equal a reciprocal lattice vector. That the reciprocal lattice vector is a vector that connects individual sites in reciprocal space. And just here I wanted to show that this Laue condition, which hopefully many of you have heard about in solid state physics, is actually completely equivalent to the Bragg condition. And that can be seen from the fact that if we divide this triangle here, we just cut it through at angle theta. Like the 2 theta is cut into theta and theta. Then Q can be written as 2k sine theta, and that has to equal G, and G, the reciprocal lattice vector length, by definition has to be integer multiples of 2 pi over d, where d is the spacing between lattice planes. And then, by knowing that it's about elastic scattering, so the length of in and out k vectors are equal, and by definition the k vector is 2 pi over lambda. Then we can set, and k is given here in this equation from our triangle construction. Then by combining these 2 equations, we find exactly the same condition which is the Bragg condition. So yeah, this is just to maybe remind you of the Laue condition, which is equivalent to the Bragg condition, because the Laue condition is important for explaining and for like visualizing elastic scattering and diffraction imaging, which will be another topic of another tutorial shortly after the Christmas break. I think we have to stop soon. So, okay, take this just as an introduction to elastic scattering, which is the main application of X-rays, elastic scattering for structure determination, both of crystals, but also of amorphous materials. We will follow up on this very soon when it comes to applications of synchrotron radiation, but also applications of X-FEL pulses, because obviously X-FEL pulses are also mostly used for structure determination by diffraction imaging, not so much for crystal targets, but more for amorphous and even single nanoparticle targets. Anyway, this is then coming up after Christmas, but we will stop here for now, and then tomorrow start with FEL science and connect back to this diffraction imaging topic then very shortly, very soon. Okay, thank you for your attention. We reconvene tomorrow. It will be about introduction to XFELs, and then on Thursday, finally comes the Python tutorial. So have a good evening and see you tomorrow.
Thank you, sir.
Thank you, sir.
See you tomorrow.
Thank you, Professor.
Tomorrow. Bye.